Hello student, I am Professor Nilesh Sheth and I have to teach you Unit 3 of paper 304 as well as Unit 3 of paper 305 for the semester 5. Now let's start with Unit 3 of paper 304, that is based on digital electronics. The title is Circuit Analysis, Design and Flip-Flop. For this, a reference book is Digital Principle and Application by Malvino and Leach. It's an international edition. So in SEM 5 and SEM 6, the digital electronics is from this book. Okay, so let's start. Digital Principle Application, chapter number 2, that is based on circuit analysis and design. For this, the knowledge of binary as well as logic gate is essential. That you have already studied in standard 12. But let's quickly revise some basic fundamental rules of this topic. Okay. A number system that we are using in our day-to-day life is a decimal number system. Why it is called decimal? Because it has 10 basic digits, 0, 1, 2 up to 9, and base of the number system is 10. This number system we are using in our regular life, but in digital electronics we don't have to use decimal number system, we have to use binary number system. In binary number system, there are only two digits, 0 and 1, and base of the number system, that's why base is 2. Now here 0 means low level and 1 means high level. There are only two levels, either low level or high level. So you have to keep this thing in your mind, that if there is a 0 means low level, 1 that is high level. Okay, so this is about the binary number system. Okay, now let's start with the logic gate. In standard 12, you have studied about basic gates as well as universal gates. So first, basic gates. Gate number 1, that is OR gate. OR gate is a function of summation or addition, and that is represented by a symbol this. Suppose A and B are the two inputs and Y is the output, then Y equals to A plus B, because I have told you, it's a function of summation. Now its truth table is like this: A, B and Y equals to A plus B. Two input means we have 4 different cases. Inputs 0 0, 0 1, 1 0, 1 1. 0 means low, 1 means high. So in OR gate, when both the inputs or all the inputs are 0, then output is 0. But if any input is high, output is high. Clear? Copy down. Second gate, that is AND gate. AND gate is a function of multiplication. So here symbol is dot in place of plus sign. So now your truth table that is going to change. Here, when any input is 0, output is 0. Output is high when both the inputs are high. When both the inputs are high, then and then output is high. That's why it is said to be the function of multiplication. Okay, now gate number 3. That is NOT gate. It is a function of inversion. There is a single input, single output. So as there is a single input, only we have two cases, either input is 0 or input is 1. If, and as I have told you, it's a function of inversion. So when the input is 0, output is 1. And when the input is 1, output is 0. Clear? So this is about the three basic gates: OR, AND, NOT. OR means function of summation, AND means function of multiplication, and NOT means inversion. So these three are the basic gates. Okay, now universal gates. In universal gate, we have two gates, NOR gate and NAND gate. First, we are going to discuss the NOR gate. NOR means not of OR. Output of OR gate is complemented. That is the meaning. So symbol look at this is OR gate and there is a bubble. So now it become NOR. Y equals to A plus B whole over bar. Truth table. Two input means 4 cases. When all the inputs are 0, output is 1. And when any input is high, output is 0. This is very interesting case. This application we have to use in second chapter, that is flip-flop. When any input is high, output is 0. when any input is high, output is 0. This condition you have to always remember in the case of NOR gate. Copy down. Second gate is a NAND gate. NAND gate means not of AND. Output of AND gate is inverted. A and B are the inputs. AND gate bubble, so it become NAND. Y is equals to A dot B whole over bar. Here that is a dot. Output is 1 1 1 0. Now here, when all the inputs are high, output is 0. But any input is 0, either it may be single input or double. At least one input is 0, you can say that output is definitely 1. This is another important instruction that you have to remember. When you deal with an AND gate, when any input is 0, output is definitely 1. This application, again, as I have told you, you have to use in second chapter flip-flop. When any input is 0, output is high. This is a very crucial condition for the NAND gate, because flip-flops are basically designed with either NOR gate or NAND gate. So these two conditions you have to always remember when you work with the NOR gate or NAND gate. Okay. None. In 12th standard, you have also studied about the De Morgan's law. So just I will give you quickly about De Morgan's theorem. According to theorem number 1, A plus B whole over bar is equals to A bar dot B bar. Now symbolically it is represented in the following way. This is a symbol of, yes, NAND gate. Wrong. We required A plus B whole over bar. So not NAND gate, we required NOR gate. So be alert. This is now your NOR gate. A plus B whole over bar, that is NOR gate. A dot B whole over bar is a NAND gate. So this is NOR gate. Now about this one. Dot shows this is AND gate, but this is bar. So A and B are the input. So actual input of this AND gate is A bar. This is a symbol of inversion. So this output is A bar dot B bar. Sometimes it is also known as, this is bubbled AND gate. This is also known as bubbled AND gate. So we can say that NOR gate is equivalent to bubbled AND gate. Okay, A plus B whole over bar is A bar dot B bar. This is De Morgan's first theorem. Now second theorem. A dot B whole over bar. Now this is your NAND gate is equals to A bar plus B bar. This output is A dot B whole over bar. This gate is your NAND gate, and this one is bubbled OR gate. This is theorem number 2. A dot B whole over bar equals to A bar plus B bar. That means you can say that NAND gate is equivalent to bubbled OR gate. So theorem number 1 and theorem number 2, it's over. Okay. After this, one more thing, that is double inversion rule. A double bar is A. A double bar is A. This is double inversion. So this is a fundamental things that is very useful in digital electronics. Now after this, we have to study some basic rules of Boolean algebra. Boolean rules. A plus 0, A plus 1, A plus A, and A plus A bar. Similarly, A dot 0, A dot 1, A dot A, and A dot A bar. So write down your answers. A plus 0, answer may be A, 0, 1. Answer is A. See, if A is 0, then 0 plus 0, 0, and A is 1, then 1 plus 0, that is 1. So it follows the action of A. Now A plus 1. Now here answer is not A. Here answer is 1. Because if A is 0, then 0 plus 1, 1. And if A is 1, then also answer remains 1. A plus A, Answer remains A. And A plus A bar. Now this is interesting. Suppose A is 0, then A bar is 1. So 0 plus 1, output is 1. If A is 1, A bar is 0. So again it remains 1. Okay. Now anything into 0, that is 0. Property of AND gate. A dot 1. If A is 0, then answer is 0. If A is 1, answer is 1. So it copy the action of A. A dot A, again it is A. A dot A bar. If A is 1, A bar is 0. So 1 dot 0, 0. Or if it is 0, then it is 1. So 0 dot 1 is also 0. Now this is very useful when you are going to solve the Boolean algebra. So properly copy down this one. Then A plus B plus C, you can say that it is A plus B plus C. Or simply A plus B, you can say that B plus A. Same way, A dot B dot C, you can say that A dot B dot C, A dot B equals to B dot A. Copy down this too. A dot B plus C, that is AB plus AC. A plus BC, that is A plus B dot A plus C. Copy down this. So 4 plus 3, 7 rules for OR gate, 7 rules for AND gate. Now De Morgan's rule, A plus B whole over bar, that is A bar dot B bar. From this side, A dot B whole over bar, that is A bar plus B bar. Okay. Now A plus AB. How to solve this? So see, A common, 1 plus B. 1 plus B. If B is 0, then 1 plus 0 is 1. If B is 1, then also 1. So it is A dot 1, this bracket. 1 plus B is nothing, but it is 1. And A dot 1, that is A. So this rule is very useful. Copy down properly. A dot A plus B. So that is A dot A plus A dot B. A dot A, that is A, plus AB, A common, 1 plus B again. So A dot 1, and finally it is A. Normally this type of questions asked in SQ section, okay, for 1 mark. And one last one, that is A double bar is equals to A, double inversion rule, that is already we have discussed. Now on base of this, one new theorem is there, and the name of the theorem is Duality Theorem. Duality theorem is used in advanced mathematics. In digital electronics, it is also used to reduce the size of equation. See, basically our goal is to reduce the size of Boolean equation, so hence the size of circuit reduces, and that's why if the size of circuit reduces, power consumption also reduces, cost of the circuit is also reduces. That is our goal. So in this chapter we are actually, by using three different methods, we are going to reduce the size of Boolean equation. Okay, the first one, that is Boolean algebra. In this duality theorem that I have told you, it is used in advanced mathematics. There are three different rules. Rule number one: changing or sign into and sign. Every or sign is changed into and sign. I will give you the example. Number two, changing and sign into or sign. And number three, complement 0 and 1. Again, changing or sign to and, changing and sign to or, and complement zeros and 1. See the example. Suppose a plus 0. What is a plus 0? Yes, that is a. Now apply this rule, changing or sign into and. So here there is dot, or sign is replaced by and. Complement zeros and 1, so this 0 become 1. A dot 1. A dot 1 is again a. So after applying duality theorem, your result remains valid equation. In further studies, you have to use this one. Okay. Now, the last topic of today's lecture: how to reduce the size of equation by using Boolean mathematics, Boolean algebra. Two examples are given in your book. So let's first discuss these two examples. Example number 1. Copy down. Draw the circuit of following Boolean equation Draw the circuit of following Boolean equation: y equals to ab bar plus ab. So look at here, this is application of AND gate, this is application of OR gate, actually this is application of NOT gate, but at present because we are in higher level, so we can use this one. In place of NOT gate directly we can show B bar. Okay. This is a circuit of y equals to ab bar plus ab. So gate number 1, 2 and 3. 3 gates required if we use the simple Boolean equation. 2 AND gate and 1 OR gate. Okay. Now if we use Boolean algebra, then A is common, B bar plus B. What is B bar plus B? We have discussed with A plus A bar. Okay, so let's say B plus B bar. If B is 0, this is 1, B is 1, this one is 0, so 0 plus 1, that is remain 1. So B plus B bar is nothing but it is 1, and A dot 1, that is A. So by using Boolean rules, this equation is reduced to y equals to A bar. Y equals to A, and that we can represent in the following way. Y equals to A, or even you can use this one also. Y equals to A. So the work of 3 gates, in previous example we have seen 3 gates are used. The job is completed by using single gate. This is the advantage. Copy down. Second example that is given in your textbook. Y equals to A bar plus B dot A plus B. So first complete this work with using basic gates. A bar plus B, that is an application of OR gate. This is also an application of OR gate. Dot represent AND gate. A bar plus B, AB, A plus B, and your Y equals to A bar plus B dot A plus B. Again 1, 2 and 3 gates required, 2 OR gate, 1 AND gate. Okay. Now apply Boolean algebra to simplify this equation. A bar dot A plus A bar B plus BA plus BB. A bar dot A bar dot B, BA, BB. A dot A bar, Boolean rules. If A is 1, A bar is 0, 0 into 1, that is 0. You can say that BA equals to AB. Yes, B dot B. If B is 0, 0 dot 0, 0, B is 1, 1 dot 1, that is 1. So it is B. Now among these 3, B is common. So A bar plus A plus 1. a bar plus a plus 1. If a is 0, a bar is 1. So 1 plus 0 plus 1, that is 1. If a is 1, a bar is 0. So 0 plus 1 plus 1, that is also 1. So ultimately, this bracket, that is 1. B dot 1, that is B. Again, it's a job of single gate. You can solve either by using AND gate or by using this one. Again, the work of 3 gates completed into single gate. So this is the advantage of Boolean mathematics. Okay, so today's lecture is over. Next time we are going to discuss another method, how to simplify the Boolean equation. So for today's lecture, quick revision: we have studied basic gates, OR and NOT, universal gate, NOR and NAND. Along with this, we have also studied about the De Morgan's theorem, Boolean rules, duality theorem, and finally how to simplify the logic circuits. My next lecture is on Saturday, 1 o'clock. I have to teach you 2 units. Unit number 3 of paper 304 and unit number 3 of paper 305. So in every week I have to take 2 lectures. First lecture is on every Wednesday, second is on every Saturday. Okay, and the topic that we have already discussed here, I will give you the notes on WhatsApp, so you can have the print of that topic also. Okay, thank you.